Okay, so yesterday we just repeated some stuff, and then there was something new about transformations, different transformation. Okay, requirements. Yeah, I deleted everything from here. That's not necessary. Oh, I will modify this. This could be in one sheet. Doesn't matter. So, which is important? I modified this T stuff. So that was disturbing. Mirror operators are signed by M and not T. The T is a Hungarian word. So let's go to the new stuff. Okay, rotational matrices. We had so I gave example for this. Also for rotational matrices in 2D and also in 3D, you can apply for the same stuff. So you can it is not. Oh, yes. Okay, in 2 dimension, you just have this rotation. Next one will with the projector, which we have. So, wear a helmet. Okay, so I gave a very simple example. Okay. First time I talked about polar coordinate systems, and it makes things much easier for some problems. This rotation helps. Actually, you do not need rotational coordinate system. but it helps for transformations. For example, you have P1, that's 1, 1 in its coordinate system, and you just rotate this with not 30. No, 40, 45 would be fine. Then you have the matrix here. You just add 45. Cosine is, if I remember well, that's this is also this. And this is it. Yes. The worst thing when you try to correct which is good. Because this was 1, 1, 1. So this is square root of 2. So this okay, that's trivial. If you are in a 3D, and you have another polar coordinate system, then it is also helpful. Yes, it's spherical coordinate system. That's polar, that's spherical. Here there are serious problems even when I just drawing something. So what I want is in this system, I know the angles. For example, the R should be, I don't know, 1. The angle should be 45. 45. 45. Both. And then I'm curious about the coordinates. I can do Pythagoras or other calculation, but it's much simpler if I just use this. It means I have to rotate this in just a moment. The y and the x axis. Okay, so let's do it. That's 1. Oh, that's wrong. That is 0. 0, 0. 0. Then oh, and I miss 1 0 there. Great. Okay, let's see what's this. let's check, otherwise I will do something wrong. This is... No. I'm sleepy. I need coffee. Here, great.
Professor, can I ask a question?
Yes.
So the thing is that what we are trying to do is we transformed our matrix, which was 1 and 1, to 45 degree in 2D first.
Yes.
This one, right? And now we have this matrix, which is, what is it radical to, I mean, under root 2?
It's 45 and 45.
The both are 45, or one is, I mean, arbitrary? We took it by ourselves. This is the rotation matrix. One is the rotation one. 1 0 0 0 0 sine. Oh, sorry, cos alpha minus sine alpha. It is the rotation matrix, right?
These are two rotation matrices,
Two rotation
but I have to multiply them before I apply them to the vector. But I'm not sure, so I haven't finished this. So that's why I'm cheating. If you can see,
Sorry.
I do not calculate myself. So I use this calculator, and then let's check this one. Perhaps it's.
I did not get the idea of why do we need two rotation matrices.
Yes, it's very simple. Because there are, and one of them is wrong. We are in 3D right now,
Obviously, yeah.
and there is one rotation
Exactly.
around the Z axis, and other rotation around the Y axis, and both of them are 45.
So we have like root r equals to 1, alpha equals to 45, and the phi equals to 45, right?
Yes.
We took it as, I mean, we have the coordinate system like that.
Yes.
Spherical coordinate system.
Yes.
Now we have a point which is pointing towards that point in a spherical coordinate
Yes.
system, right? We have an arbitrary vector that we want to know, is it some sort of, I'm just a bit confused with the transformation of the vector. Are we transforming our vector towards that point which you mentioned? Like r equals to 1, phi equals to 45, and alpha equals to
Here in this moment there is no vector,
no,
just matrices.
matrices of rotation.
Yes, two rotation matrices, and one of them is wrong actually.
And then what about this one in 2D? We have an arbitrary.
In 2D that was a bit different because I know everything by heart. Here we had just one arbitrary point,
Yeah.
and here I rotated this point to the x-axis.
Got it.
I just wanted to show you with transformation matrix the life is much easier.
Okay, so we did not transform any kind of vector in 3D yet, but we are trying to find out the rotational matrix, which we need to transform any arbitrary vector to that point.
Yes, actually we know the transformation matrices because there is one formula for this, and there are two transformation matrices. The problem is that I was a bit disoriented, and I wanted to wait. Perhaps I'm still okay. First, I transform this around x, that's fine. Then I have to transform around z,
Yeah, that's true.
and that was not done by me.
Got it.
So this is here not good,
No.
but I will not suffer with this. And actually, so I have what I have. I have, oh no.
Well, it would be easier if you don't put the values, because there are some trigonometric identities through which you can get one.
Yeah, you are right, but I wanted to put the values. Because these are simple values. So these are x.
It's gonna land in our calculation.
No, I don't want. This is x, and then we need z, and that's. Okay, so let's start with this. It's quite barbaric that, but okay, so we have a transformation matrix, and we start from, for example, matrix, and this is now the transformation.
We did not get the Y transform. There was 3 matrices, right? In this slide.
Yes, but we just use 2 of them,
Yeah.
X and Z. Okay, this is the result. Okay, something like this. When I do coordinate transformation between spacecrafts and everything, then I have a lot of such things, and I never do it by hand. Usually I do, but this day is quite horrible. Okay, rotation. Mirror of vectors of the plan for the A per 2 line. Actually, originally I wanted to put second camera somewhere, but finally I just had this stuff. It's better if you see what I'm explaining. Okay, here.
It's quite clear, to be honest.
This one, this is okay, I will do this, but I wanted to try a special projection. Maybe next time, and we will not finish what I wanted to do. I will pass these meetings on Wednesday.
Yeah.
It would be arbitrary to be there. I will ask a remote online participation or something like this. It's not acceptable. Okay. So the aim of these practices are to understand better the theoretical material. So we have in 2D a line. I'm perfectly dumb, help me please. What is the sinus of 30? It's 1/2.
Yeah,
Okay.
yeah.
I'm cannot 1/2. So there is a line alpha is 30. And this should be the transformation matrix for this. It means if there is a vector, quite simple vector, then the result should be something like this. No, it's yes. Okay, this is what I expect. Yesterday I recognized something weird in the Hungarian class. With you, we could finish everything related to vectors. With them, we could not. But I gave the same practice in Hungarian also, so they had all vector operations and everything. But no one told me, we haven't talked about this during the lecture. And also, the thematics, the syllabus of the Hungarian class for the same subject, for the same course, are different. It's different than yours. I don't know why. Doesn't matter. So now, sorry?
Which one contains more information or their contains more information?
It's the same, but for you, we start with matrices, then determinants, and then other things. They start with vectors, more vectors, some tricks with vectors like this angles between vectors and distance between points and so on that we had last semester, and then we switch to matrices.
Yeah, that would be a fine approach, I guess.
Yeah, but we did this when you were absent at the first course. We did it.
Yeah.
Okay, here, let's see this. So if I have, this is what is it? It's mirror, and you cannot see a thing. I will throw them in the trash, and after a while, perhaps I will find appropriate pens. What's this? Okay, so 30 degree. One and one. Oh, how much is it? It's something. I'm right?
Yeah.
Okay. Okay, so this is the transformation matrix. Let's check this. proper. No, no. Yeah, yes. Yes, it was good. However, I don't think it's.
Isn't the minus supposed to be on the sign and not cosine?
What sign?
Ah, yeah, it's a different one. Not nothing.
Mm. Okay, it seems to be good. The numbers are quite weird. So this transformation did the mirror for this line. Just it's weird a little bit. Okay, I didn't do anything with this, not yet. Let's have a point. simplest. And the plan would be the xy, so it's normal is this. So it suggests that the tensor this is the identical matrix minus 2. So it means minus 1, minus 1, minus 1. And everything else is 0. This is good. I do not need to do any test with vectors. We can understand this. All vectors, the mirror of all vectors, for example this one, is minus of the identical vector. I hope so. At least I try something. I think no.
Why did we took this minus vector, minus identity?
Here.
Here, yeah, minus 2 and...
so if I... oh, thank you. That's a mistake. That's a mistake. It's not 0. It's not 0 at all. It is minus 2 everywhere else. So this is not good. And then it's both a test.
It's going to be minus 2 diagonal, right?
Sorry?
It's going to be minus 2 in the diagonal only, isn't it?
No, so it is everywhere.
I did not get the identity matrix is minus with 2 and is an arbitrary matrix, right?
It's not arbitrary matrix, it's from the normal.
For the normal, okay. Normal means perpendicular, okay. Perpendicular to what? To the vector, right? Because I is the identical matrix minus 2m. What is this m?
The n is the normal of the plane, and the plane is the xy plane, the axis of xy plane. So the normal is z. So it means 0, 0, 1.
Okay.
So if I do the multiplication, then it's 2, and I have to check something. For me, not. For me, something is odd. Sorry, it is in Hungarian. Here. The problem is that the operation, this n times n transpose, is not a scalar product. I think that's the problem.
And in the formula, there is no 2n multiply n transpose.
No, there is a 2 in it, but not. This is the problem. Problem is.
There is 1 over 9 there.
Wait. The problem is.
Here is 1 over 9. I don't know why 1 over 9 is there. And there is an arbitrary matrix 2, 1 minus 2.
Wait. 4. Then Okay. Problem is the following. This, oh. Without any warning, here, in this formula, the normals, this is not a scalaric a scalar product. The scalar product would result a scalar, and I would multiply a scalar from the ID matrix. So it means this would be a wrong operation. The reality, this should be something else, and that is did I talk about the dyadic product?
Direct delta.
No, not direct delta. Dyadic product of vectors. I mentioned it, but
I think you mentioned it, yeah.
we didn't do anything with it.
Yeah, we don't do anything, yeah.
We didn't do anything. Now it is the time, unfortunately, and actually the time is over, so sorry. Okay, so one this is not not 100% sure, but that's the dyadic multiplication, and then with that it's 1 minus 1, and that seems to be good. That's good. So if I said that's good. This is it. Okay, sorry. So the dyadic multiplication there means you go a place in the matrix, you take this element and then multiply this element. Then you come here, you multiply this element and this element. So just go through and do for all elements of the vector are multiplied all elements of the other vector at the place. Is it okay?
Yeah.
Okay. Then it creates this. I will modify this, and this is wrong in the book. It should be somehow emphasized. It's a dyadic product. And then this is a matrix. You have the the formula. That's an ID matrix. Everywhere everything is 0, minus 2. And this is good. Why good? We have this is good, but not the task. One minus 1. That's good. So from this, you will have this. The x, y are the same. The z is the opposite because it's mirror. So it works.
Finally, Professor, what's the name of this product?
This dyadic.
Dyadic. What's
The dyadic.
Derek, Derek,
I
come
show
on
you.
again.
I show you. Just a moment. Uh-oh. Okay, it is not here, but it should be.
Excuse me, Professor.
Yeah, the time is over.
Yeah, we have a
Yeah, I know. You can go. Thank you. But if you are curious, I just find the. It's here. The addict product. It is here. The addict product. Sorry for being late. Sorry for being so messed up. See you next week, and thank you. I will upload everything to the Teams, and we will continue next week. This one. Thank you. I also have another lecture.
Sure, I also wanted, if you have a few minutes, I would like to ask you about the cube set.
Yes, okay.
Which topics you can offer me if I want to do thesis with you. I studied a bit about it, and it would be good for me if it
Okay. Just a moment. I want to